everyone. Today I will walk you through the code we have developed for a network congestion prediction system using simulated network matrices, LSTM-based deep learning, and ns-3 for network simulation. Okay, so let's dive in. Well, the goal of this project is to predict the network congestion based on real-time matrices like throughput, latency, packet loss, and more. This is important in 5G and modern networks to ensure smooth performance and allocate resources efficiently. Well, overall, this has two major components: network simulation using ns-3 to model network traffic between nodes, and second, congestion prediction using an LSTM based deep learning model. Okay, so now we will move to the code. Well, okay, node and channel setup is right here. Okay, so node container nodes creates two nodes to simulate a network. Point to point helper configures a point to point channel with 5 Mbps data rate and 2 millisecond delay. Network device container, it represents devices installed on the nodes, and internet stack helper, it installs the TCP IP protocol stack on nodes, and there's a IP address here. Then there's the application setup. Okay, so server UDP eco server helper is installed on one node to simulate a server listening on port 9. Client UDP eco client helper on the other node to send packets to the server with specific parameters. Simulation execution, the server starts at 1 second and stops at 10 seconds, while client starts sending data at 2 seconds. Okay, so now network matrices, this is all the dependency and requirements we need to have. Okay, so the purpose here is that this function right here, this generates synthetic data to mimic real world matrices of the network, and this is the code for this. So let me show you right here what does it eventually generates. Okay, so what we see here is that the throughput normally distributed around 100 Mbps with a standard deviation of 15 Mbps. Latency normally distributed around 20 millisecond with the standard deviation of 5 millisecond. Packet loss uniformly distributed between 0 and 5%. Active users random integers between 50 and 200. Bandwidth utilization uniformly distributed between 40% and 90%. Well, what we see as an output, it returns a data frame with 5 matrices and their respective samples. So now we have data preparation for LSTM model. Yes. Okay, so here, so scaling features include like the input features, throughput, latency. These are scaled using the standard scaler to normalize values for better model performance. And we have also created sequences in 60 timestamps. Yeah. So for each 60 step sequence, a congestion level is calculated based on whether the throughput is below 70% or not. It is right here what I'm conveying, and it returns X sequences which represents features, and Y labels. This Y represent labels, and this is all the sample generation and the graph plotting of the functional graphs. This is the 50 epochs which we have run. The main thing which I'm trying to show you here is the build model. Wait, let me see. Okay, so yeah, this is the main. Okay, so model layers, LSTM layers, two LSTM layers with 64 and 32 units to capture temporal patterns in the data dropout, used after each LSTM layer to prevent overfitting by randomly dropping neurons during training. And dense layers are fully connected with 16 neurons to feature extraction, followed by a neuron output layer with a sigmoid activation for binary classification, whether it has a congestion or no congestion. And optimizer we have used is Adam for adaptive learning, and loss binary cross entropy for binary classification task, matrices accuracy to evaluate performance. And this is the model training, right? Where is that? Okay, yeah, main training sequence. Yeah, so input data, the training data, x train comma y train is used to fit the model. Epochs and batch size, we have used 50 epochs with batch size of 32 samples per training step. And we have also reserved 20% of the training data for validation during training to monitor overfitting. And testing, yeah. Okay, so here we have used the testing and prediction. Okay, a single test input, for example, throughput of 85,5 and latency of 25.3, etc., is repeated for 60 times. 60 time steps to match the model's input shape. The trained models outputs a probability. Well, example we have here 2.71 congestion probability, and we have saved this model. And okay, where is the result? And we have also got some plots. This is for the model loss and model accuracy, and this is for all the other matrices which we have drawn from the code. This is the plotting for the same. Thank you.